So I won't do the whole thing, but I'll point you in the right direction. We want to know if this integral converges or diverges. Before we get there, check this out. 5 compared to 5. If I divide this 5 by 4 and this by 3, which fraction is now bigger? Well, this one's about 1.25, and this is about 1.6 repeating. So you can see that this is bigger than that. This is greater. But you know what? I could have told you that without doing this, because if you have numerators that are the same, then whichever has the smaller denominator is going to be the bigger fraction. Because you're taking this and you're splitting it into fewer pieces, so each piece will be bigger than the one that's broken up into more pieces. So general rule of thumb, if the tops are the same, you find the smaller bottom, the one with the smaller denominator, produces the bigger fraction. So now here, I want to compare this to something else. So that is exactly that. Now notice the difference here. I have removed the x. So watch, this x is positive because x goes from 0 to 2 pi. So this denominator is bigger than this one. This one is smaller. And because this denominator is smaller, this fraction is greater than that one. So I'm going to say greater or equal. But you know what you can do when you compare? You could compare this to something else. So what about this? What about if we just compare this with 1? The bottom, I'll keep it the same. But now let me change the top. What's bigger between 1 and that? Remember that sine is bounded. Sine is bounded between -1 and 1. It doesn't matter what it is inside of the parentheses. The angle inside doesn't matter. I don't care what you put in there. Sine of whatever is going to be at most 1 or at smallest -1, which is why 1 is greater than or equal to that, and the bottoms were the same. But now if I compare this with something else, what if I just compare it with x? So x plus 1 is bigger than x. X is smaller. So this denominator is smaller. So this whole fraction is bigger, especially because the tops are the same. So that's what I want to do. And you know what? Maybe we could keep going and comparing it to something that's easier to look at. The reason I did this sequence of comparisons is because this looks easier than that. So what I'm trying to do now is maybe I can take this guy here. If I can show that this integral converges, if I can show that the bigger one converges, then the smaller one has to also converge. So anytime you pick something that's bigger, you want to show that the bigger converges. Because if the bigger converges, then the smaller must also converge. So if you can figure out this integral, and if this integral is an actual number, then it converges and the smaller converges, the original converges. But if you do this integral and you get back like infinity, which means that this diverges, then we have not reached a conclusion. Because the idea is if you pick a bigger function, you show that it converges, which forces the little guy to converge. If you pick a bigger function and it diverges, that tells us nothing about the smaller function.